Hello everybody, this is project 3 of my engineering projects. In this video we'll be going over my robotic arm. So after this quick demo we can get into all the steps it took to build this. So now let's get into the components I used to build this project. First we have the Arduino Nano. Its adapter cable. The Hyleco PCA 965A motor driver. The L2 98N motor driver, 4 MG996R servos, the NEMA 17 stepper motor, five angle rotary cinches, a breadboard, around 25 pin-to-pin wires, around 20 pin-to-hole wires, and finally, some extra coiled wires. And now we'll go over the main circuit. So although this does look a little disorganized at first, it's easy to understand by breaking into three parts. We have the controls right here, the potentiometers. Then we have our motors for the joints and the motor driver that's connected to all these, that's connected back to the board. Then we have our stepper motor control with this L2 98N motor driver and this NEMA 17 stepper motor right here. And basically this is going to be the base joints. This motor driver connects to all the joints. This motor driver solely powers the stepper motor. And then these potentiometers all control the each motor. We have 5 potentiometers. And now I'm going to quickly demonstrate and show you what this looks like. And before I do this, it's hard to see, but basically this black wire right here is connected to ground. This yellow is the analog input, and this red is the 5 volt. So now if we take a closer look at these motors, for example, this one, this is going to be for the shoulder of the motor, the robotic arm, and because it has 20 kg of torque, so it's going to be the strongest, and since it's going to be holding up these 3 joints, it has to be the strongest, and this is why I have a 20 kg motor for it. Then we have 3 normal MG996R motors, servos, and these are just for the elbow, wrist, and claw. And then of course stepper for the base because it's the strongest. And then from there we have our Arduino Nano, and then our connections to the motor that connect to the stepper, and we have our external battery source that's for the PCA 9685 motor driver. And now I'm going to do a quick demonstration of our circuit. So the first thing I'm going to do is grab a piece of tape and then place it onto this stepper. And then you should be able to tell the other joint motor's fine. And now I'm going to use this wire with its hole and then this potentiometer, and I'm going to move it and watch as one of these motors will spin with the potentiometer. So you can see here, since it's not tethered to the ground, it's going to be shaking a bit. But you can see how I move it back and forth. It works like that. And now if I, for example, have a different motor like this, it moves back and forth as I go down. And then if we find the stepper motor, you can see how when I move it this way, or if I move it around back, it spins whatever way I move it. And this is going to be one of the main features of the robotic arm. And basically I'm going to have a control panel that contains each of these potentiometers. And with that, you're going to be able to move a little dial that I'll 3D print, counterclockwise or clockwise, and then the motor will spin corresponding to the rotation angle. And so now you can see if I move this back and forth like this, so we have this, and then that's really the main principle of the circuit. And that's really all there is to it. So with that, now we can get into the CAD and the thought process behind the CAD. So now, here's the CAD of my project. So first, before we get into the individual parts, here's a quick rundown of the final product. So here are all the 3D model parts. So first, obviously we have the arm, and I just put everything together without any of the motors in the CAD or steel ball bearings at the bottom, so it just looks like it's floating right now. But then I just roughly put together a quick sketch of what it should look like after the final product, hopefully. And then now we have a quick sketch of the control panel with the dials mated to the holes on the panel. And that's really all there is to see for this final product. So hopefully it looks like this, but now let's get into the individual parts of the control and body, and then we can get into our final product. So first we have our control panel. So for this, I just want a relatively simple design. We're going to put the potentiometers that control the motors on the bottom, and then hot glue those, and then use dials at the top, and then hot glue the rods in the dials, which look like this, to through these holes, and then connect them up so it creates a spinning dial that can control the motor, and the motor will move with the dial. And now if we go back and we head into body, we have the base, and so for this we have our stepper motor inside the stepper motor wire trail to go connect back to the motor driver. And then we have our top, just has a space for the shoulder to elbow motor, and then an axis for the stepper motor, which I measured out. And then we have our shoulder to elbow arm. This connects from here to the elbow to wrist, right here. And then our elbow to wrist connects so this will connect to this motor that would be in this volume that was removed from the sketch. And then this is the wrist to claw section, and this right here is connected to the removed volume right here. And then we have our claw section for the moving part of the claw, and that's going to be right here. So this motor axis right here is going to connect to the motor that would be in here. And then this stationary, as you saw in the final sketch as well, is going to be connected to this right here. So it creates a kind of clamping effect. So this motor right here, let's say the mouse is the top of the moving part of the claw, so that's going to go like this and then clamp the object into the stationary part of the claw, and then that's what creates a tension to pick it up or pick up an object. So anyway, that's about it for the individual pieces. And then again, hopefully it looks like this as the final product. So now that we've gone over that, we can get into the CAD parts, and then we can get into the final product. And now here's the code for this project. So it was relatively simple, only about maybe like 100 lines. And so first we have our libraries included. So we use just the WireH library, the library for the PWM motor driver, and then the library for the stepper motor. And by the way, the stepper motor that I used again was the NEMA 17. So anyway, first we initialize some parameters related to the control of the servo motor. So we have our servo min and max PWM, and as well as this initializes the PWM servo driver. And then now we're doing some more initialization, but this time for specifically the stepper motor, because it's a little bit different than the 4 other servo motors in the robotic arm. And so first, this is just a parameter that was specific to my servo motor. And then here are the 4 digital pins that I connected the stepper motor to. And then now we have our stepper motor control. So A0 controls stepper motor, and then a stepper initialization, so our first and last value 0, and the stepper pop value represents the potentiometer value of the potentiometer that is corresponding to the stepper motor. And then we have our motor speed. We'll get into this in a bit. Then we have our min and max speed, and then our threshold. And basically what this threshold does is it will come in later, but the main idea is the potentiometer has a lot of noise. And so originally when I was building this project, the stepper motor kept jerking left to right, and the threshold made it so basically the potentiometer had to change by 50 values, or else it would not move at all. And this helped get rid of most of the noise from the robotic arm. And you'll see this at the end if it's not making sense. So now we have our setup. So we're just initializing serial, and then we begin or start up the PWM motor driver, and then we set the frequency. This is common initialization. Then we have our stepper motor initialization. So we set our last pot value to the stepper motor pot value, and that would just be A0, and it would be whatever it was when I turned the robotic arm off, or when I just unplugged it and left it. And then we have our delay 10 for 10 milliseconds, and then this just lets the servo motors boot up. And then we have the main code in the loop. So first we just set all the new pot values, and this represents the 4 pot values for the 4 servo motors, or all the joints in the robotic arm, of course except for the stepper motor. And then we have our corresponding analog pins, and I could have made this a bit more organized, but it ended up just being this way. And then potentiometer values. So basically what this does is, all it does is it constantly sets through this loop. It resets the servo motor's positions. So like when I'm moving a dial on the control panel, this is what makes the motor change to that corresponding position. And then this initializes all of the PWM signals for the servos connected to the motor driver. And now this is everything down here is just related to the stepper motor control, because it's a little bit more complex. So first what this does is it just reads the stepper motor potentiometer value. So first this reads the stepper motor potentiometer value, and then this finds the potentiometer difference in a loop, so it's constantly finding the new difference between the original and the last. And then once it finds this, we grab the absolute value, that's what this ABS function does, of that pot difference, and then check if it's over the threshold. And if it's over the threshold 50, then basically what it's going to do is it's going to move in the corresponding direction through these if and else statements. So if it's over, then it's going to step to the left or clockwise, yes, and then if it's under, then it's going to go counterclockwise, and then it would print also the motor speed. And I was doing this to test something out earlier, but now that's not really relevant anymore. And then it steps the stepper motor actually moves with this function right here, and then last pot value is then reset. So then we could continue this equation through the loop, and then that completes the loop. And then also this removes any overlay for the motors for one motor. So like if you change, then change it back, it won't glitch out or anything, and it will just delay it by about 100 milliseconds. And I found that this was the most effective time. So anyway, that's about it for the code. So with that, here's a quick time lapse of some of the 3D printing. And so finally, after designing the circuit, designing all the parts, printing them out, writing all the code, here's the final product. So with that, thank you for watching, and more projects coming soon.